Hello everyone! How many times have you finished a CFD simulation in OpenFOAM, the solution converged, but then you asked yourself, what now? How can I turn all this data into something meaningful, like pressure and velocity contours, streamlines, or even useful plots of physical properties? If that sounds familiar, then this video is for you. Hello again, and welcome to Automated Engineering Solutions. I am Dr. Ahmed, and in this video I will show you how to post-process your 2D airfoil CFD simulation in OpenFOAM using only open source tools like Python and ParaView. Before we start, if you are interested in CFD simulations using free software, make sure to subscribe for more tutorials, and don't forget to share this video with your friends who have the same interest. So let's get started. In my previous tutorial, I showed how to set up and run a CFD simulation for a 2D airfoil using OpenFOAM. In this video, I will use the same case as an example to demonstrate how to perform post-processing, turn your simulation data into meaningful engineering results. I will also leave a link to the previous tutorial and the complete project folder in the description below, so you can follow up step by step. In this case study, we use NACA 2412 airfoil at angle of attack 10 degrees and Mach number 0.3. Before running your simulation, it's very important to define all the variables you want to monitor and extract, both during the simulation and after it finishes. This ensures OpenFOAM automatically records the data you will need later for analysis and post-processing. Now go to your project folder, open the system directory, and then open the control dictionary file. This file controls how your simulation runs, including when to start, when to stop, and what kind of data to record during the run. Now scroll down to the end of your control dictionary file and add this function section. This part tells OpenFOAM what data to extract automatically during the simulation. The first function we will add is the wing forces section. It calculates the forces and moment acting on the airfoil surface. Make sure you write the correct batch name exactly as it appears in your boundary file. Otherwise, OpenFOAM won't know which surface to monitor. The second part of the function is used to extract the pressure values on the airfoil surface. This function samples the pressure on both the upper and lower sides of the wing every 100 time steps. We will later use these pressure values to calculate and to plot pressure coefficient, which shows how the pressure varies along the airfoil. Now save the control dictionary file, then open your terminal, navigate to your project folder, and run simulation using the simple foam solver. Once the simulation starts, OpenFOAM will automatically record all the forces and sample pressure data we defined in the function section. Here we go, the simulation has finished successfully. We can now see the output of force function showing the force value acting on the wing due to both pressure and viscous effects. In the project folder, a new directory named postProcessing has been automatically created. Inside this folder, you will find two main subfolders, one for forces and another for sample pressure. The forces folder contains data files that records the aerodynamic forces and moment in the three directions separated into pressure and viscous contributions. The sample pressure folder includes raw data with the coordinate of the sampled point along the wing and their corresponding pressure values, which can later be used to plot the pressure distribution over the airfoil. Now we go back to our project folder and create a new Python script for post-processing. We will name it post.py, and inside this file we will write down 5 main functions to calculate all data we need. The first function reads the forces.dat file generated by OpenFOAM. It extracts the time history of pressure and viscous forces and then sums them to get the total force component in the XYZ direction. The second function uses those forces value to plot the convergence history. This helps us to confirm when the simulation reached steady state by showing how the total force evolves with time, and whether the solution is converged or not. The third function calculates the lift and drag coefficients based on the total forces, air density, free stream velocity, and reference area. It saves the time-based CL and CD values to the text file for further analysis. The fourth function reads the sample pressure data from airfoil surface. It filters the data at a specific z-plane, calculates the pressure coefficient, Cp, and then plots the pressure distribution along the chord, giving us a clear picture of suction and pressure regions on the airfoil. Finally, in the main block, all these functions are called in order. First to plot convergence, then to compute lift and drag coefficient, and finally to generate the Cp distribution plot. Once done, all results are saved automatically in the post-processing folder. After finishing the code, save the file as post.py, then open the terminal and run it using the command python 3 post.py. The script will automatically generate all the mentioned plots and result files inside the post-processing folder. Once everything is done, it will display the message "All post-processing complete successfully." Now let's go to the post-processing folder and check the generated files. First, in the wing forces folder, you can see the force convergence history. As you can see, the solution has converged over time. You can also find the calculated lift and drag coefficient values as a function of time, including the final lift and drag coefficients value. Finally, in the airfoil sample folder, you will find the CP plot, which shows the pressure coefficient along the chord, highlighting the pressure and suction side of the wing. I would like to thank you all for watching until the end. Stay tuned for part 2, where I will explain the qualitative post-processing result. If you enjoyed this content, don't forget to hit like, subscribe, and share the video. Your support helps me bring more CFD tutorials and engineering solutions to the channel.